Saxon Algebra 2, Lesson 11. We have two topics today, one algebra, one geometry. We're starting with the algebra. The topic is adding fractions. Now I hear what you're saying. You're saying, adding fractions? I've been doing that for years. Come on, lady, what new do you have to say about that? Okay, I agree. You have been adding fractions for a long time and you probably are extremely good at it. What we're going to focus on now is adding fractions that are mostly letters rather than numbers. And it's not a lot harder, but it is a little different. So that's why we're taking a good look at it. Let's just jump into the first problem and I'll explain as we go. Good girl, Grace. You can sit. If you don't know, Gracie's my dog. She's an Irish setter. She looks like a bear. If you Google cinnamon bear, you'll get a pretty good idea of what she looks like. Copying the problem. And we see, yeah, it's definitely alphabet soup. A lot of letters, one number that's a numeric coefficient, and a couple exponents. Everything else is letters. All right, the first thing that we do when we see that we have fractions, the very first question we ask ourselves, is this an equation or an expression? Because our answer for that will dictate for us the strategy that we're going to take to solve the problem. Now, an equal sign is the sure indication that you have an equation. I see no equal sign. So that tells us that we have an expression, not an equation. And you know, they're not really good or bad, they're just different. If we have an equation, we can make the denominators go away completely. We can blow them up, destroy them, clean slate. Oh, now I have a cat meowing at me. Hello, kitten, are you hungry? Hi. I have a tuxedo cat. His name's Sirius, like Sirius Black in Harry Potter. He's gonna have to wait though. I'm sorry, little man. Okay, we do not have an equal sign. That means we have to give up hope of destroying these denominators. The best we're gonna be able to do is make them match, right? So if we have an equation, we can blow them up. If we have an expression, all we can do is make them match. That's the best we can do. In order to make them match, what we're gonna do is multiply top and bottom, okay? We'll talk about equations when we get to those, but these we're gonna be multiplying top and bottom to get the bottoms to match, and then we'll smush it all together and see what happens. Okay, so now we know our strategy. The next step, and by the way, the step is the same no matter which of these we're doing, we find the LCM, the least common multiple. The way that we do that is we start with the first. It's actually easier when you have a bunch of letters than numbers. We start with the first one, 2a. Then we ask, can the second denominator find itself here? The answer is no, right? There's no way, we don't see, we've got the a, but we don't have the x squared. So we add to the things that we're multiplying here. We add factors for whatever's missing, right? We need the x squared. Now he can find himself within this LCM. How about this one? Well, he can find his a, and he can find two of his x's, but we need to add another x here, so I'm going to make that a 3. Now there's more than enough x's for him, but there's just enough x's for him. All right, so that's how we build an LCM. We go down the list and we look to make sure that each of these denominators can find themselves in the LCM. Okay, beautiful. That's what we want our denominator to be. In order to get it there, we multiply each denominator by the missing piece to make it equal to the LCM, right? And this is just like doing it with numbers, just a little weirder. Here we've got the 2a, we need the x to the third. And if we multiply the bottom by x to the third, we have to multiply the top. Here we need a 2, the front 2, and we need one more x. So this one will be multiplying by 2x, top and bottom. Here we have the ax to the third, that's all good, we just need the 2 over the 2. Make sense? So we multiply it by the missing pieces. Now we're ready to do all that multiplication and squish it all together. If we played our cards right, all of the denominators are perfect. We don't have to worry about them anymore. We now turn our attention to the numerators, and we're going to multiply. I'm going to put things in alphabetical order with any numeric coefficients first, then all the alphas. So here I'm going to have kx to the third plus 2bcx plus 2m. Notice I'm just changing the order of these things. When we're multiplying, order doesn't matter. All of these are being multiplied, right? There's no adding going on. We're all multiplying. That looks good. There's nothing to distribute up here. It's nice and clean. There's no like terms. So I'm pretty happy that we've reached the end. And then I write my common denominator down here on the bottom. And look, we got it right. Just double checking, yeah. Okay, so just to finish my steps, first we decided if it was an equation or expression. That tells us our multiplying strategy. We found the LCM. The next step is to multiply each fraction, top and bottom, by the missing pieces. And I did that in green, right? It's this, and this, and this. Those are the missing pieces, so I'll circle that word here. And then the last step is to simplify. This is what always happens to me. I get excited about writing out the steps in the beginning, and then I get all involved in the problem, and I forget. Oh, it's so sad. All right, let's do another problem here while we've got our steps in front of us. Example 11.2. Now, I didn't write this exactly the way John did because he made this B float in the middle here. You know how I hate a floating letter or number like that. I don't like it. I instinctively bumped it up so I could put it over a 1. Okay? That's how I would copy this. I wouldn't write it, I wouldn't copy it exactly as it's written in the book because I don't want floaty letters. I want to make them into a fraction right away. All right, let's go through our process again. And this is the last of our problems on this topic. We need an LCM, don't we? You can call it a least common denominator because the denominator is where we're working. I like to call it a least common multiple because I want to remind myself of that word multiply. I can only build a least common multiple by multiplying together chunks. Sometimes, depending on the denominators we're given, and it's not the case here, sometimes we're tempted to add. Can't we add something? But we can't. We can't add. We can only multiply. So that's why I always call it the least common multiple. All right, we start with the first one. K. Yep, that's good. This one's a 1. It's got no opinions at all. So, yeah, there's always a 1 in there. This one is more complicated. So we're going to have to make our least common multiple equal to that. So I'm going to make it AK squared. Now he can find himself. He's still in there. The 1 is fine. He's just a middle child that's a go along to get along kind of guy. That's my take. I'm a middle child. Okay, so now we've got, and I didn't even do the first step. My bad. Again, we have an expression, so we know that we're going to be adjusting top and bottom. We can't make the denominators go away. All right. Now we're ready to multiply by the missing pieces. We compare the LCM to what we have, and we multiply by what's missing. This one needs an AK, right? And this one needs everything, AK squared. And this guy is fine as it is. So you can think of it as multiplying it by 1/1, or you can just think of it as it's fine. We don't have to do a darn thing. Now I'm ready to multiply. Again, I'm gonna go alphabetical. So I'm gonna have AKM minus ABK squared plus CX. Some students might ask, well, should we factor the AK out of these two? Since we see there are matching letters in these, we could factor out the AK. It is not necessary to do that. Factoring and distributing are neither right nor wrong, so you can leave them in either form. We can't add them together. They're not like terms because they have other letters mixed in. Sorry, I yawned. So what I recommend at this point is leave it as you found it, then check the answer. If John has done some sort of factoring or something, then you can say, all right, how can I make my answer look exactly like his? But if you were giving me a test, or if I was giving you a test, you can give me a test too, then I would accept this as a perfectly fine answer. All right, and then our denominator, we made them all match. It's AK squared. And that's our final answer. Yay. Now, what's interesting is that I've been using my notes from last year. I just have them open on the table with my textbook as I'm doing this because it helps me format my pages. I like to organize it, so it looks a certain way. So I'm using last year's as sort of a guide. Sometimes I change it up. I make it better than last year's, but I have that notebook open. And over here on last year's page, I have Galloping Gertie. Here, I'll show you. See, it says Galloping Gertie. That was the nickname they gave to the old Tacoma Narrows Bridge. Because remember, you may have heard this story. They built it. And then shortly thereafter, after its construction, there was a big windstorm that swept through and it just twisted and turned that bridge and destroyed it. It's a fascinating video to watch. It's really old school. I think it was in the 50s, maybe the 60s that it happened. But they do have footage of that bridge going nuts. I don't know why I was talking about Galloping Gertie in doing this problem. I'm trying to retrace my mental steps. I have no clue, but it's a really cool video. So I'm going to find that and I'll link it for you in the description again, which is kind of my new favorite hobby. But it's just a cool video. It doesn't have anything to do with math that I can think of now. But I saw that note and was like, huh, that's kind of weird that I was talking about Galloping Gertie. I don't know why. Does any part of this problem remind you of a twisting, broken down bridge or a giant windstorm? I don't see it, but who knows what I was thinking. Okay, now we're moving on to our geometry topic. The name of that topic is Inscribed Angles. Now, I hate to be that person who's like, and in the Latin, this means, but it's really helpful because a word like inscribed is just a big, weird, vague word that we don't really know. But scribe means to write. So what these angles are, these inscribed angles, are written, right, inside. When you know that that's what this word means, it makes it a lot easier to remember what the heck we're talking about. Because an inscribed angle fills the whole, this is an inscribed angle. It's on the edge, the vertex of the angle is on the far edge, and then it goes across like this. This is an inscribed angle. As opposed to this, an angle that starts at the center of the circle. This is called a central angle. Now, you'll notice that both of them hit the edge of the circle like so, right? And I tried to make them look about the same. That's called the intercepted arc. In my brain, I think of it as the bite. If you see this as a Pac-Man, which P.S. I do, if you see that as a Pac-Man, then that's the bite that he's taking out of the circle. This is what we call the central angle, okay? And in these, I'm just making up numbers, I don't know that these are true. The central angle is the same size as the intercepted arc. Huh, all right. But in an inscribed angle, the intercepted arc is twice as big as the angle. Ah, okay. So that's interesting. So this gives us a really interesting relationship. We can say that the inscribed angle equals 1/2 the intercepted arc, right? The inscribed angle is half of the intercepted arc, right? 15 is half of 30. Or we can say it the other way around. We can say the intercepted arc equals 2 times the inscribed angle. Right? We're saying the same thing twice, we're just saying it in opposite directions. This information is going to be very helpful to us in setting up some problems. All right? So I'm going to flip my page in just a second, but I'll give you a minute to finish getting this. These diagrams, to me, explain it better than the words, but the words help too. So inscribed angles are written on the edges. Now to me, this is a Pac-Man, right? Because the bite comes out of the middle. This is a Teenage Mutant Ninja Turtle with his mask on, profile shot, right? His little eye would be right there. There'd be a knot here. The little ends would be hanging down. This is a Teenage Mutant Ninja Turtle. Teenage Mutant Ninja Turtle. Okay? Central angle is a Pac-Man. I think he's hyphenated, isn't he? Okay? That will help you remember the difference. Teenage Mutant Ninja Turtles are way more nuanced and complex than Pac-Man. Pac-Man just runs around eating things. Teenage Mutant Ninja Turtles have rich inner lives, and that's why they have a more complicated number scenario here. There, how's my metaphor? Do you like it? I'm happy with it. Okay, next page. Let's do a problem. There is just one problem to do. Ready? Here we go. Circle. John's got a bunch of theoretical stuff written in here to prove to us why this is true. We don't care. We don't care. I don't care. And if I don't care, I'm pretty sure you don't care, because I generally care. Okay, here we go. We have a line here, we have a line here, and it says 40 degrees. Now, before I write anything more onto this, I go, okay, look, it's a Teenage Mutant. Shh, shh. There's the intercepted arc, right? I know I can figure that out. I'm excited about that. There's more to write down, but I'm excited because I understand what to do with that. Now we're told that this is 5x. It's written like that. Don't let those parentheses freak you out. Remember that they're just there because John's saying that the degrees, the angle, this arc rather, it's not an angle, it's an arc. That is, the measurement of that is 5x. The degrees relates to the whole thing, not just the x. So we have to put parentheses on it. From here to here, it is 7x plus 40. So we're getting the measures of some of the intercepted arcs, right? And we're supposed to find x. Well, what do we know? X is here, X is here. How far is it from here to here? I don't know. But I do know that all the way around would be 360. I know that this part, we could subtract from the 360 because it's the intercepted arc of this angle, right? So I could subtract, how much would we subtract? 40? No, this is 80 degrees, right? I started right 40. It's 80 degrees because the angle is half of the arc. The arc is twice the size of the angle. So this is 80, this is 40. I know that this plus this does not equal this. So if I subtract the total circle minus the part that I'm not interested in, that gives me 280, right? Let me just write this. The arc equals 2 times the angle. I'm just going to write that down so you remember how we got that 80 right here. Now I subtract 280 is this much. So I can say 5x plus 7x plus 40, I'm not worrying about parentheses because it's just addition for days, equals 280. Oh, look what we did. We made a fun little algebra problem to solve. Now I'm just swimming fish and combining like terms. 12x equals 240. And we get x equals 20. Notice that this answer is just an algebraic answer. It's not the measure of this intercepted arc or this one. We would have to put x in and multiply and solve those, wouldn't we? So we don't have to put degrees by this because this isn't the measure of anything. It's just an algebra answer that fits into this picture. Another way that you could set this up, and it might fit better in your brain, is to say, okay, once I know this is 80 degrees, I could say 5x plus 7x plus 40 plus 80, that's the whole circle, right? This is another way to set this up. I mentally subtracted the 80 first and set this equal to the rest of it, but this is another way that your brain might see it better. And we would solve it and we would get the same answer because we would just subtract the 80 and the 40. Well, let's just show you. This adds to 120, right? So we would subtract 120 and then we would combine those like terms and we would get 12x equals 240, which is the exact same thing we got there. X equals 20. So same answer either way. It's just a question of what jumps into your brain faster. All right, that is our friend lesson 11 done. In the practice, there's a problem exactly like this, So set it up the very same way. And you might even want to do that one first before you forget how to do it. All right, yay, lesson 11 is over. Goodbye.